Hello and welcome to this video about my project titled The Implementation of a Modular Framework for Reinforcement Learning with Neuro-Evolutional Neural Networks. The project gives an introduction into reinforcement learning and neuroevolution with practical examples through a framework that is implemented on the PixelFlux service. In this video, I will go over the framework, looking more closely at the code and components to showcase their inner workings. I will do this mainly by talking through some of the examples given in the framework repository. Regarding the documentation of the project, all necessary files are kept on the GitHub called Neuroforcement. This includes an extensive README about the methods used, the interactions, as well as a list of dependencies and a general setup guide. Quickly browsing over how to get started, log into either the RedFlux or GreenFlux servers and run the startup.sh to connect your home drive and to update the proxy settings. Having completed this, navigate to the directory of your choice and upload the framework files and folders. If the repository is made public, one could also use git clone for this step. Before examining the code and other components, let us look into general reinforcement learning and its terminology, so that the rest of the video is easier to understand. First off, reinforcement learning is a subfield of machine learning that teaches an agent how to choose an action from its action space within a particular environment in order to maximize reward over time. At its core is this agent-environment interaction shown here, which already introduces the main components of any reinforcement learning problem. We have an agent, which is the program that we train, and which decides to take certain actions. The actions get sent to the environment, which causes its state to change. The environment is the world, real or virtual, in which the agent is. It sends back a reward for the action and the new state in which the agent finds itself. Overarching this single interaction is the so-called episode, which is a repetition of this interaction from an initial state to a terminal or final state. Now let's look at how this interaction can be represented in code. First, looking at a pseudocode representation. Most importantly, we need an agent and an environment. However, for us humans, it's nice to have a way to see the environment and the performance of our agent, which can be shown visually. Given these three components, we also need a main script to handle the interaction. So a general problem works like this. We first have to initialize the agent and the environment. Then for each episode, decide to reset the environment and find an initial state. Then for each step of the episode, so from initial to terminal state, we need to send the state to the agent. The agent decides on which action to take based on previous experiences. Then this action is sent back to the main script, which sends it off to the environment, which transitions to a new state and also assigns a reward to the action. This is then sent back to the main script, where it can be further sent again to the agent for the next step, and also can be used in visualization so we can see what's going on. Now looking at the framework. The framework includes a Jupyter notebook called examples IPYNB that showcases what this main script looks like. For the different solution methods, we will look at this file in more detail a bit later. In the modules folder, we have three files that represent our components. For one, our agents.py, which includes functions that represent the solution approaches and which is the part of the framework that learns and suggests actions to take. To realize the environment, I used OpenAI Gym, which is a toolkit that provides a wide variety of simulated environments, but the RL environments.py includes some further manipulation for some specific interactions. And then finally, the visualizations.py includes functions that allow OpenAI Gym to render inline in Jupyter Notebook through the use of a virtual display, and which has some functions to display the agent's learning development in a plot. Now I will go through a few of the examples to showcase these interactions. They are all set up in the same way. The first code cell includes the training loop, in which the agent explores the environment and learns to navigate it. While in training, the agent still does random actions sometimes to help explore the whole environment and to avoid getting stuck in loops. At the end of the training, the progress is saved in one form or another in this training folder, which the next code cell then loads to see how successful the training was. The first example is the frozen lake toy text problem and the use of Tabular Q-Learning. This is still very basic and helps with understanding the fundamentals of reinforcement learning. The basic interaction stays the same for all approaches, just becoming more complex each time. Specific to Q-Learning is the Q value. which is the value given to a certain state action pair derived from the reward received in a previous step. The Q function is the function of the Q value over all the available states in the environment. The Q function is what the agent needs to find, since it's like a roadmap to solving the problem. So let's first look at this on a higher level. So we have our main interaction as we've seen it before. However, now the agent is the Tabular Q-Learning method and the environment is the Frozen Lake toy text example. So here, Tabular Q-Learning represents its Q function in a so-called Q table, which has as rows the different states and as columns the different actions. So given any state, it can look into this table and find the action with the highest Q value associated to it, and that represents the Q function for Tabular Q-Learning. The Frozen Lake environment is a grid world environment where the agent starts on the letter S and needs to move to the letter G. It can move to the right, up, down, or left, and needs to walk over the letters F, which are representative of ice spheres that are in the lake. And if the agent walks over the letters H, it falls into the water and the episode terminates. As a visual output, we have a representation of the episodes and the action we've chosen, as well as where the agent is walking. Now finally, let's look at what this looks like in code. So first of all, we define a total number of episodes. So this is the max amount of episodes that the agent can take to learn the Q table in this example, since we have the Tabular Q-Learning agent. Then we have a max amount of steps, so the amount of actions the agent can take each episode, we set that to 400. Then here we define the environment, which is just a call from OpenAI Gym. So we let the Frozen Lake environment be created. Then we set up our agent, which is a function that is written in the framework as the Q-Learning agent with all its parameters. Then for each episode, we reset the state. So just do an environment reset, which is also an OpenAI Gym function. And we reset the number of steps to 0. And while this step counter is below our max steps, we send the current state to our agent, which then gives us back an action. If this action can either be up, down, left, or right, or random, in the case if the agent wants to explore the environment. If it is random, we just use this OpenAI Gym function to sample a random action and assign that action value. And then we use this env.step action, which is also from OpenAI Gym, to execute this action. And this then returns the next state, a reward for that action, and a done flag. So if this done flag is set, the episode is terminal. So after that, we can't play the game anymore. And then we send all of this information to our agent, which then uses it to update its Q table. Then, of course, we move on to the next state. So we say our current state is the next state, and we add a action, our max step counter, we add one to that. And here, if the done flag is set, we break out. So then our episode is basically terminated. And this repeats for the total number of episodes. Then finally, our agent has this Q table, which we then print out so we can look at it. And we also save it so we can load it for later. So it's saved in this training folder. So if we now let this run live on the server, we can see that the agent finds this Q table, which gives it a roadmap to solving the environment. And as we have already saved that Q table, in the next cell, we can use this training. So this is literally just creating an agent, loading the Q table that we've already saved, and seeing how it walks over our environment. So in here, the red piece is the agent as it's moving, and we can see that it solves the problem each time. This is nice for small and simple problems that do not have too many states. However, looking at more complex problems, it quickly becomes impractical to store all the Q values in a table, as this will become gigantic. So we need to somehow approximate the Q function. This is where neural networks come in. They are used in conjunction with Q-learning in a method called DQN or deep Q-learning. So let's again first look at this on a higher level. So here we have our known diagram, and we can see that now our Tabular Q-Learning agent has been replaced by our deep Q-Learning agent. which now represents the Q function with a neural net, so it approximates the Q function. This takes as input the state and outputs an action to take. And for this example, we also use a more complex example, which we can also render live on the server. And this is called the cart pole problem. In this problem, we can control the cart, so we can move it either left or right on a rail. And the aim of the game is to keep this pole balanced, so to keep it in an upright position. And for this, OpenAI Gym has a state representation, which is a vector that includes the cart position, the cart velocity, and the pole position and the pole velocity. All right, let's see what this DQN agent looks like in code. So first of all, I'm already going to start this training loop. This is the training loop as we had it before. I'm going to start this since we have quite a number of episodes to run through, as this is much more of a difficult problem, so it takes way longer to learn. And I'm going to not be explaining all of the code, but the most important functions that have been implemented for the framework. So first of all is this display, which starts the virtual display, as the cart pole problem is an actual rendered problem. So if we want to look at how our agent is performing in real time, we need to use the virtual display. Then again, we have this gym.make function from OpenAI Gym, which creates our environment. Then we call the DQN agent observations function, which has been written for the framework, which creates our neural network, which in this case represents our agent. Then finally, we have again our familiar episodes loop. So for each episode, we first reset the environment to find the initial state. Then while true, so if the episode has not terminated, we output each frame. So this is a function which takes the current env.render, so takes the pixel data from OpenAI Gym and displays it on our virtual display. And for each step, we again input the state into our agent.choose action, which is just a forward pass through our neural network. That in turn gives us our action. This action we then send to the environment with this env.step function from OpenAI Gym again. This returns the new state, the reward, and the done flag, as was previously stated as well. Then finally, we execute this agent.learn function, which uses the experience the agent has had in backpropagation on the neural network. So the weights and biases are updated. And then we have this moving on one state. So we set the current state as the new state. And if the done flag is set, we break out of this loop, as we've been accustomed to. Then finally, the final step is we save the network parameters of our trained agent again in this training folder. And I can see already that the agent has already completed it this time. So the network parameters that we've saved in training, we can now again use to create that network that we've saved and to see how our training went. So this is just what this cell does. It just creates a network with all the weights and biases from our training. And as we can see here, the agent does perform quite well with our environment. And if you're wondering why it stops at 200, the base version of the cart pole problem is programmed to stop at a maximum reward of 200. So you can, at maximum 200 steps, the episode terminates anyway. So if it reaches a score of 200, then our agent did perfectly. But we can see it does quite well with an average reward of 160. So in deep Q-learning, we've now used a neural network to approximate our Q function to solve a more complex problem than we could with the tabular Q-learning. But the question is always, what is the optimal network or neural network structure to solve our problem? This is where NEAT comes in. NEAT is short for the Neuro-Evolution of Augmenting Topologies, which is an approach of testing various different neural network structures on a given problem to see which one is the best. So let's first again look at the principles of NEAT on a higher level. So we have our trusted diagram that we've looked at for each approach so far. What changes now is that instead of only having the one neural network that we had for DQN, we now have a generation of networks. So we have different networks that need all tests on the environment. So it doesn't just do this one, but it tests out the environment on each network structure each time, each episode, and sees which one is the best and tries to evolve a better network out of those tests. So networks that are performing better get a higher compensation, or they are used for evolution. And this then in the end finds you a better network structure which can solve the problem. So it's kind of brute forcing the network structure that can solve the card pole problem in this case. So here we also have a little bit of a change that the NEAT reporter is introduced, which is just a functionality that the library which is used to implement NEAT has already built in. So this is a good way of showing what NEAT is doing in the background. So now finally, let's look at the NEAT code. Before doing anything with NEAT, one needs to first install the NEAT Python package on the server, which is the package which has all the functionality which is required for NEAT. So because the NEAT Python package is used, and because NEAT is used in general, the loop that we've implemented before doesn't stay the same. So we have a different workflow in this example, but we can break it down so it kind of makes sense in the way we've seen it before. So first of all, for NEAT, we need to define a evaluation function for the genome. So a genome is generally just a singular network. So where we had a generation which has many different networks, each network there is a genome. So we first write a evaluation function which tests every genome, so every network in that generation on our problem. So this function runs an episode for each specific network in that generation and goes through all the different genomes or networks in that generation, and then it sends the results back and some evolution happens, and then we start all over. So then a new generation is created and all the genomes in that generation are tested again. So now let's look at the rest of the code. So we have some familiar functions like the gym.make, which creates the environment, and the env.reset, which resets the environment back to an initial state. Then what happens in these lines of code is that we are loading a config file, which NEAT uses to set all its parameters. Then the next function call creates the population based on the config file that we've loaded. So all the different parameters get loaded into a population, and we call this population P. And these functions down here allow us to display certain stats about the different generations and how they are doing. And finally, this is the most important one. This is how the algorithm defines a winner. So in this p.run, we send our evaluation function that we've defined on top. So that tests each different genome on the environment. And here we send it a number of different generations. So in this case, we let it run for 50 different generations. And then from that, it runs and tests and evolves networks for 50 generations to see which one does the best. And finally, we print the best winner and also save the NEAT winner structure in the training folder so we can load it in the next step to see how well it plays the game. So saving the winner from 50 generations of evolution, we can just load this network structure of the winner because it's been saved into the trainings file again, and we can see how well it plays the game. So in this case, we can see, or we should see, that the agent is very stable, it plays the game very well, and it always reaches 200 steps, or a reward of 200, which is the maximum amount it can get. And we can also see comparatively to DQN, it's also much more stable. So we have examined 3 solution methods and their implementation in the framework on the PixelFlux servers. First, Tabular Q-Learning, which stores the Q function in the form of a table for simple problems. Then DQN, which can be used for much larger problems through the use of a static neural network as a function estimator. And finally NEAT, which explores different neural network structures to find the best one to solve a given problem. Thank you for your attention. I hope you enjoyed this insight into my project. I hope this gives a good baseline for reinforcement learning and neuroevolution at the Hochschule Karlsruhe that can be built upon and used in other projects in the future. As a final remark, I would like to thank Mr. Bauer for his guidance and input during the project. I enjoyed working in the lab setting, which gave a good outlet for intellectual discussion during times where personal contact was hard to find. Thank you.